Good evening and welcome again to my science channel. What I'm going to try and do is I'm going to do a series of two presentations. They're going to be astronomy based because I want to do some astronomy ones and expand the science part of my channel a little bit. And where these two presentations are ultimately going to end up is with Edwin Hubble, with the Hubble constant and cosmological expansion. So what I wanted to do first of all is actually familiarise you with some astronomical units and units that we use in science and engineering, some that you might not be familiar with. So just to make sure that when we do talk about Edwin Hubble and that, you do know units of measurement of distance and the units of measurement of temperature you're familiar with. So first of all, let's talk about temperature. We're all familiar with degrees C and degrees F, centigrade of Fahrenheit, but what William Thomson, Lord Kelvin, did was to make a temperature scale starting off at what we know as absolute zero. And absolute zero is where you've got pretty much no energy there and some really weird phenomena start occurring. So how does that look? What is absolute zero? Well, absolute zero is minus 273 degrees centigrade there. And then each Kelvin, and it's not degrees Kelvin, it is just Kelvin. And one increment in Kelvin is the same as a degree C. So what you can see here is at 0 degrees C, the temperature is 273 Kelvin, and that's where water freezes. We're all familiar with that at 0 degrees. And then 100 degrees C, there's water's boiling point, and as we said, a Kelvin is equal to a degree C. We can see that the Kelvin is 373. So that's the boiling point of water is 373 Kelvin, 100 degrees C. So that's what it looks like. But when we're talking astronomical terms, how does these sort of temperatures look? Well, when we look at the temperatures of stars, or for instance, our own sun, we can see that the inner core of the sun is going to be 15.5 million Kelvin. Now, if we looked at that on a Fahrenheit scale, that would be 28 million degrees Fahrenheit. So that's pretty warm. And then looking at the outside, now that's the core temperature of the sun. But if you look at the outside of the sun, just the upper levels of it, then what you're getting there is 5,780 Kelvin, which is considerably cooler than the core, even though that's still pretty warm. But at 5,780 Kelvin, that is still really hot, but in comparison to the center of the sun, it's pretty cool. And the gases at these temperatures behave differently. So it will emit certain wavelengths of light here, and in the outer atmosphere of the sun, it will actually absorb different pieces of light. And that's something we're going to expand upon when we talk about Edwin Hubble. So that's temperature done with for the moment. What I want to look at now is actual distance. Now, a lot of distances in astronomy are set around the speed of light. Now, how quick is the speed of light? Well, it's actually 186,000 miles per second, or 300,000 kilometers per second. So that's a good number, but what does that mean? Well, if you were standing on the surface of planet Earth at a particular point, and a piece of light passes you, by the time you count 1 second, it goes 1, 2, 3, 4, 5, 6, 7.5 times around the world. 1 second. So that is really pretty quick, indeed faster than Usain Bolt. Everything is sort of geared around that, and what I want to have a look at now is a light year. And some people think that a light year is a measurement of time because it's got a year in it, but it's actually a measurement of distance. So what I'm going to do is let's just break some of these distances down. So the speed of light is 300,000 kilometers per second. So that's 186,000 miles per second. So how far does the light go in that period of time? Well, a light year is 9460730777119.56 kilometers. So that's a fairly long way. Now, to start breaking that down a little bit more, we have what's called a parsec. And a parsec is 3.26 rounded up to 3.3 light years. And that's equivalent to 19 trillion miles. But we go even one step further than that. We got a megaparsec. On a megaparsec, so anything with the term mega in it means a million, like a kilo is 1,000, or a deca is 10, and a centi is 100, a mega is a million. So a megaparsec is 3.26, once again rounded up to 3.3 million light years. So there are some of the distances that we need to be familiar with in astronomy and the mathematics that is involved in astronomy. So let's have a bit of fun with calculations. First of all, let's think about Star Wars. And in Star Wars, Han Solo said that his ship made the Kessel Run in less than 12 parsecs. So what I want you to think about is if the Kessel Run is 12 parsecs long, how far is that in light years? Okay then, so if we have a look at Han Solo's journey in Millennium Falcon down the Kessel Run, which is 12 parsecs, we're going to convert that to light years. And we know that there's 3.3 parsecs in a light year. And I'll simply multiply by 12, because there's 12 of them. So that's going to equal 39.6 light years. And the second question tonight is, Andromeda is a galaxy, M31, and that's 2.5 million light years away. So what I want you to do is pause the film for a second and convert those million light years into megaparsecs. Okay then, to convert the distance that Andromeda is away from us into parsecs, we get the 2.5 million light years, which is the distance the galaxy is away from us, and 3.3 million light years per megaparsec. So we divide the one by the other. We don't have to change any units because they're both in millions. That's millions of light years, and that's megaparsecs. So if you divide 2.5 by 3.33, the answer we get is it's a distance of 0.75 megaparsecs away. So I hope you enjoyed a little delve into measurement and temperature and measurement of distances in astronomy, and because you tell Kelvin in engineering that as well. The next time we meet, I will talk about Hubble, and we'll use the units that we've learned today in that talk. Thank you very much, and stay safe.